Welcome, Dr. Joshi. I'm going to hand the mic to you.
Thank you very much, John. Yeah, so I'm more of a sort of formal verification, formal methods guy. Primarily, Sam talked about new features in Move as a language. I am more of a user from the formal verification perspective, and I'm just going to, this is a high level motivating talk about formal methods. It's been now more than 20 years since I got introduced to this fantastic research area. I was a faculty member in one of the top tech schools in India, IIT. Some of you might have heard it. And then, yeah, I'm with Supra right now. Without further ado, let's jump right in. This is a very small piece of code, hello world. All of us start our programming journey with a hello world code. And if somebody asks that, is this program correct? People can keep on wondering, try to find some syntax error, etc. And now look at the magic that I'm going to do, okay? I'm not going to change the program itself. What I'm going to do is just write one comment, and suddenly this whole program becomes incorrect, right? It's syntactically correct. That's not what we intended, right? So the first lesson that when we say that something is correct or not is to be able to define that what do we mean by correct. So let's take a dive a little bit into the history. So these two gentlemen over here, Sir Tony Hoare on the right, on the left, Dr. Robert Floyd. Dr. Robert Floyd is also famous for Floyd-Warshall algorithm. So these two, they came up with this mathematical system, and they formalized that how does one reason about program correctness. And this was the work carried out in 1967 to 1969, and for which both of them got CM Turing Award, which is Nobel equivalent in computer science, right? And yeah, Sir Tony Hoare, he's the same person who invented null reference. So he says that it's $1 billion mistake by him. The man who gives illness, the same man giving you cure by providing this whole mathematical framework to formally reason about programs. Let's talk about what is a formal specification. It's a formal description of sets, and formal is the keyword over here. Sets of state or behavior of the program or program fragment that defines correctness. We have to first define that what it means by the program to be correct for the state program at a given program point. And so with this idea in mind, I think that there was this sort of interesting language that was created called IFIL, which is, they call it correct by construction. And he's inventor. He has this very nice code that our field can use, make use of more formality, but we haven't really realized it. Right. So I'm going to abuse programming notations here, and please pardon me for that. But it is not that the formal specification is something very alien to us. We have been actually using it via assertions, right? So what does an assertion tells you? So a programmer tells by assertion that say, look, when the program execution comes at this particular program point, what I want to happen is that whatever the state in which the program is in, that state must satisfy this condition. Now, if you see that I'm abusing notation, and if I say that, okay, just transferring some amount from to this subtraction over here, even though maybe initially it might look like, yeah, this is correct, balance from minus amount should be greater equals 0. But if the amount is very high, this can actually cause underflow, right? And thankfully, Move as a programming language, they have runtime check. So yeah, so let me just correct that. Basically, the correct way to specify if you want to do the assertion is just say that, okay, whatever the balance is there in from is greater or equals amount. So let me just talk about, we are talking about formal description of sets, right? So let's talk about set of states. So what is a program state? If you take just one variable, which is U64 variable, how many different possible values that are there for this variable? 64 bits, so 2 power 64 program states are there. And that defines the state space of the program. And now we can think about program, even a simple one-line program that is x is equal to x plus 1. We can think of them as state transformers, which takes a state and it transforms into another state, or takes a set of state, transform into another set of states. For example, if the input state is x is equal to 0, this program fragment is going to transform into x is equal to 1. And we say that, okay, this is fine, it's not a problem. And we can keep on doing this till if x is a 64-bit U64, we can keep on doing it till this point, and this is all safe. But when you come over here, that basically there is this one value for which the overflow is going to happen. And for most of our application logic, we really don't like overflows, etc. And maybe that's a bad behavior. We say that this particular input state is not acceptable for this program, because then the behavior of the program is not correct, right? So we can then generalize this thing and we say that, okay, this is my precondition. Precondition is nothing but a set of constraints. These constraints actually define set of states. That these are the set of states. If you give me as a program, what I guarantee is that once my execution completes, I'm going to guarantee you that I'll give you the output state which satisfies these set of constraint, or essentially my output state is going to be inside the set of state defined by the post condition, right? And now this thing saying that, okay, if it is strictly less than max, then this is strictly greater than 0. We can actually refine it further by saying that no, it is not any arbitrary value which is greater than 0, but it is exactly the value 1 greater than what you gave me as the input value, right? So it's a stronger post condition because it gives you a smaller set. So looking at the original transfer program that we talked about, we can write precondition and post condition. Again, I'm abusing notation. This is not how you do it in Move. You have a spec block for a function. But so here the precondition, I'm saying that, okay, you have to transfer some amount. You need to have balance greater than the amount that you want to transfer out. And at the end, after the transfer, what you guarantee is that the new balance and the amount that you have transferred out must exactly be equal to old balance in the from account and the other way around in the to account, right? And it seems that, okay, that's fine, but there is something missing in this specification, and which is this, that if both of these addresses are same, then the post condition is not going to hold, right? And doesn't matter what amount you give. Either you can refine your precondition by adding this, or you can weaken your post condition by saying that only if the address is not equal to each other, only then you enforce these things, right? And now you see that the addresses are, let's say, about 32 bytes, 256 bits, right? That means that if, let's say, that I do testing, uniform random testing, you pick from a uniform random generator, you pick values from these 2 power 2 56 different values, and run the module that I just showed you. The number is so large, the state space is so large that before your tester can find, even if it's an exascale computer doing 10 power 18 tests, it's going to take 10 power 51 years, which is 10 power 41 times the age of the universe. That testing is just not going to cut it, right? There could be just that boundary condition which we can miss via testing. And this is the example that I gave you. It's not an arbitrary example, because things like this can happen in real life, and this is the exact example. So this is the code. Now, to the best of my knowledge, what I know is that nobody really exploited this code. Some white hat hacker reported via responsible disclosure method, and this was fixed, right? So what's the problem here? There are a bunch of tickets. For every ticket, first, it is checking that all of the tickets that is being submitted is by the owner, and it's also checking that the lottery ticket is not already claimed for reward, right? So it is being checked. Once those checks are done, you calculate all the rewards, make the transfer, and here, this particular function, multi-claim reward, is over here, where inside a loop, it sets all of the tickets to be as claimed, that, okay, so that you cannot claim second time. Now, the problem is that what if you are passing array of tickets, but what if they are just exact copy of each other? They are not unique tickets. They are not different. It's the same value. So that means that if you have one winning ticket, you can actually claim the reward multiple times, because you are not setting your flag setting to true in this for loop, right? So every time that you check that whether a particular ticket is claimed or not, it's still going to be false. And then you come over here. So this is a real life example that not checking this uniqueness and things like that, input validation, if it's missing, it can actually cause problems, right? So one thing is that they probably could have done that before you mark that something is claimed, you need to ensure that this is not claimed already, right? Or alternatively, and this is I'm abusing the notation, is that what is the invariant? What is the post condition after which, that we always want to maintain whenever somebody is claiming, right? So we say that, okay, these are the total winning tickets and their corresponding reward. And that money should exactly be equal to the reward money that is already claimed and the reward money that is unclaimed, right? You need to do it that for all the unclaimed tickets, what should be the reward, etc., right? So if that had been the post condition, this bug could have been found. Yeah. So why this thing happens, right? So there is a fundamental limitation of testing is you have, when you say that you are taking this input, there are, as I said, that your input state space is very huge. So in the testing, you pick one point from this entire input state space, and then you run your test, and then says that, okay, it's all green, it didn't fail. Okay, let's run another test, and let's run another test, and we can run billions of such tests. We say, okay, let's ship it out to production, right? Once we ship it out to production, then this happens, that the input state that we didn't consider, we didn't test it for it, it fails, right? And that's the fundamental limitation, that testing, just because there is no failure during testing doesn't mean that the program doesn't have bugs. So what do we ideally want, right? What we ideally want is that instead of taking one state at a time, what we want to do is that just take the entire input state space and see exactly how the program is going to, each statement of your program is going to transform into another set of state and another set of state, etc. And then what you want to find out is that the final one, whether it is all green or whether it intersects with the red. That is what you really want, right? But yeah, unfortunately, this problem is undecidable in computer science. But we are engineering, just because something seems well, etc. Okay, let's do approximation. Let's try our best effort. So what people do is they say that, okay, because computing this exact set of states and transformation could be very costly. So what you do is that you compute approximation, and many times computing approximation is easier. And these are all over approximation. So then by over approximation, you do this. And if your over approximation is also all green, that tells you that even when you have taken a larger set of state, the program still doesn't fail. So obviously, since your actual input state space is going to be smaller, it's not going to fail. So that means that it's a proof that your program is safe. But there is a bit of a glitch over here, that sometimes what can happen is that the set of bad states that you have defined, that okay, this is bad for my program, it can intersect not with the actual set of states that are reachable, but because you have done this over approximation, so it can intersect with the yellow region, and then so it's a false positive because it's going to raise an alarm, right? So in testing, what is happening is that you always start from inside the input state space, and here in this approximate symbolic reachability, you over approximate. And ideally, what you want to do is that you want to enlarge more and more the under approximation part, and you want to make over approximation smaller and smaller. One can wonder that how do people do this? So we can start small, take a very small program fragment for which you know that, okay, this is the precondition, after which if you run this program, you are guaranteed to end up in the set of state that gives a post condition. And you have another statement for which you can define your pre and post condition. And if these conditions are such that the precondition of the second one is large enough so that the post condition of the first one fits inside it, it's like a fitting two blocks together, then you can say that I can guarantee that this new program, which is P1 followed by P2, when you start from pre1, you are going to end up in post condition of 2. And this is how you build this proof of safety from starting from small and bigger programs. It is not that this is a panacea, right? There are things to watch out for. Right? As I said, that if your initial set of state that you started with is inside the precondition that in which your program is going to behave correctly, then it's fine, right? Because here in this example, the bad state is outside of post condition, so it's safe. But if you are not careful enough in writing your precondition, so what can happen is that the checker can check only on the intersection of the actual initial set of state and the precondition. So you have missed this red part, which is actually a valid input for your program. But in your reachability part or in your proving part, it cannot reason about this red region because you have defined your condition to be too small, right? So when the post condition is large, you usually end up in a false positive. But if your preconditions are too small, you may actually miss some real bugs. Now, thankfully, and this I really like, right? For most of the programming languages, so I myself have designed symbolic execution engine. I have contributed to CBMs, one of the industrial strength model checker, participated in SVComp, did wonderfully well, etc. But this is usually the community that builds these checkers or provers, etc. It is a separate community than the programming language designers. But here, it's a fantastic surprise that it's not an afterthought that, hey, we should have some formal analysis tools for the language. And it's a brilliant part about Move is that you have something like Move Prover. It's an entire specification language and it's very expressive. You can express precondition, postcondition, loop invariant, and you have quantifiers and things like that. It's quite expressive. And yeah, this is more of a wish list that I wish that there were a few more things that is there. So reasoning over loops, it's very tricky on Move Prover because there are some very good techniques reasoning over loops. They are not right now embedded inside Move Prover. Loop acceleration, loop unrolling is there, but you have to manually specify, and then key induction and things like that. The second one that I'm talking about is, I think maybe this feature is there, but it's undocumented because I see this in some programs, but in most spec language, if I want to define at intermediate point, a specification variable. So maybe it's there. I'm not sure. It would be better to have these things. And this is third thing is also about loops, right? It always relies on a person to supply the loop invariant. It would be good that there are algorithms like Houdini or interpolation based techniques. Some of them are there. So right now, I think most of the time it has been designed in a fashion that, okay, you know what, you just run prover for, I think default timeout is, I don't know, 40 seconds or something, and that's it, right? I come from usually the world where actually because the system is very critical, right? You are verifying code of aircrafts and things like that. You run it for days, such tools like these provers, etc. And that's where you can actually then afford to have this sophisticated algorithm built in so that you are not really relying on programmers' expertise that much to specify the correct invariant and things like that. But nevertheless, I think that having a prover, formal prover from the same team as the language designers, that's a fantastic thing about a language, right? Because it's not an afterthought, the correctness about the language. And I'm not really saying that testing is bad, right? Testing has its own advantage. It can scale to millions of lines of code. You can still test, and it's very easily understood by most of the people, the community, etc. And there are lots of tools and libraries available. Now, these provers and formal methods, on the other hand, requires expertise, and if you do it correctly, usually by abstraction, etc., there are no false negative. I put a star, terms and conditions apply. And yeah, there is a bit of scarcity of tools and library. But the thing is that testing, when something fails in testing, you definitely know there is a problem. When you are able to prove via these provers, etc., and if you are over approximate really, then it's a proof that there are no bugs, there are no corner cases, and things like that. And yeah, I really admire Joshua for the encouragement that we take this kind of rigor very seriously. For example, Supra's moonshot is formally verified industrial strength protocol. And yeah, so it has a lot of advantages that, we find that there are a lot of bugs mostly happen because of some corner case that we missed. And that's where using formal method alongside testing can go to a great enhance the quality and the safety and the security of the Web3 world to a great extent. And yeah, I would be happy to collaborate with the community on these aspects. I'm really passionate about these things, and thank you very much for listening to this talk.